Good morning.
Good morning. I'm sorry I'm a bit late.
Oh, no problem.
Yeah. So can I share my screen?
Yeah, I think we'll wait just a couple more minutes. We have a slide up right now that's kind of like an intro slide for us for the
Oh,
seminars. You can
okay.
probably see it. And when I start introducing you, Tracy will stop sharing that, and then you can feel free to share your slides.
Okay. Thank you.
And so you go by, is it Nachi? Am I pronouncing that right?
Nochi is the best.
Nochi. Okay.
Mm-hmm.
And can you say your last name for me?
It's Acharya.
Acharya. Okay,
Yeah.
thanks.
People confused with Acharya and Acharya because most of the people call me Acharya, which is different.
Acharya. Okay.
Yeah. So I'm sorry. How are you, Katie, today?
I'm good. Yeah, I'm kind of bouncing back and forth between a couple of Zoom meetings today,
Oh yeah.
as we all are, I'm sure.
Life is full of Zoom nowadays.
Yeah. Well, we're just at the top of the hour, so if you're good to go, I can start the introduction.
Yeah. I think we
Cool.
can start. Mm-hmm.
Welcome, everyone. Thanks for joining us for the next iteration of our CGD Seminar Series. Very pleased to introduce Dr. Nachiketa Acharya, who is our seminar speaker today. Dr. Acharya is an associate research scientist at the International Research Institute for Climate and Society, which is hosted at the Earth Institute at Columbia University. His research specializes in subseasonal to seasonal climate forecasting, its application in managing weather and climate risks, and developing climate services for developing countries. He received his PhD in statistics from the Utkal University in India in 2014. During his PhD, he worked in a project funded by the government of India on developing an extended range forecast system for climate risk management in agriculture. After his PhD, he was a project scientist at the National Center for Medium Range Weather Forecasting, also related to the government of India. And he was a postdoc at the City University of New York, working on the effect of climate change on New York City's water supply. He joined IRI in 2016 and works on the seasonal climate forecast system, performing calibrated probabilistic seasonal forecasts for precipitation and temperature. More recently, he has been developing IRI's experimental subseasonal forecasts. And so today he will speak to us about, does non-Gaussian calibration improve multi-model seasonal forecasts? So Nochi, take it away. The floor is yours. You can share your screen.
Thank you, Katie. Thanks a lot. Let me share my screen. Yeah, shall I start?
Yes, go ahead. It looks good.
Okay. Thanks everybody for joining today. And yes, as Katie mentioned that when I joined IRI, my main work is actually to change the IRI existing forecast system. And like it's kind of like 3 years from now. So I learned a lot actually in terms of how to use the right calibration method for each of the variables. So that's what I like today. I'm just sharing my experience and try to give some idea about how we choose the calibration method when we are talking about seasonal forecast. So today I'm mostly talking about seasonal forecast, but I'm using almost the same system for subseasonal. So that may be for the another topic for another seminar, but today I just concentrate on the seasonal forecast. So the motivation is very clear, as we know that for making any kind of forecast, whether it's seasonal or subseasonal, we cannot actually use the raw output from the GCM because it has some systematic bias or some random bias. So if we just make it a very clear equation, we can say from GCM we can get a signal. We can also get an indirect signal which is bias and some chaos. And that indirect signal may be in terms of linear errors, or maybe the wrong interpretation of the reason behind the rainfall or temperature, or most of the cases which we found is actually the wrong representation of teleconnection with ENSO and the rainfall. So there is a number of reasons to have this indirect signal, and obviously the main, like, the solution is like improving inside the model. But as you know, like, modeling uh, system is not so easy to that we can just incorporate any kind of correction and we just run tomorrow. So that's what, like, the statistical post-processing actually very important. And this is one example, like, for certain point of world, like, you can, if you just plot a model and observation, you can get this kind of mismatch kind of signal from the model and the observation, and we can simply see like there is some error in terms of the magnitude, but there is also an error in terms of the signal, so, or the patterns. So we have to correct those models in such a way that we can actually include that incorporate the observed signals, as well as we can remove the systematic bias. In that sense, IRI is kind of pioneer, because in, I think, in 1995 or 96, IRI started making real-time forecast. But from the very first forecast, IRI have a mission to actually incorporate the calibration on the seasonal forecasts. So in that time, we ran two-tier, which is atmospheric model, and then we can kind of doing lots of calibration, and it was start from somewhere in the Bayesian, then we go with the principal component regression. So like so many different kind of method we started throughout the time. So that was like a system up to 2017 April, before I joined in IRI. And then we have a new system. So I'll comment new system, but the new system is actually based on all the one tier or couple ocean atmospheric model based on North American multimodal ensemble project. So instead of running the model in-house at IRI nowadays, we're actually collaborating with the NMME project, and we are the official host of all NMME models. Maybe some of you are using those models from our data library. So we thought like we are anyway you are hosting the model, so instead of running our own model, why not we use all those state of art models? So that was like whole background to change the IRI system. And then the easy thing come in our mind that, okay, so we can just do the same kind of calibration, whatever we used to do it, like, kind of principal component regression or kind of spatial pattern based, where you actually correct the deterministic signal from the model and then convert it in probability based on the normal distribution. So that was like my job, and I thought, oh, that's so easy. But the problem is, like, earlier the model we ran, we have a lots of hindcast data. That means we have at least 50 years of data from the past. So that 50 years of data from the past help us to build a robust statistical post processing. But for the NMME, we don't have that liberty. We have such a short hindcast. So we, from that, we thought that we have to change our post processing method too. So this is like the new system. So I can just give you one simple a table instead of explaining all whatever in this table. I just want to highlight the main thing. So as I explained, like earlier, we have like pattern based correction method, mostly Gaussian method, but now we introduce called extended logistic regression method. I will come back on that method after. But the interesting improvement also, we used to have 2.5-degree grid forecast. Now we have 1 degree, because NMME is all 1 degree. And you also, earlier we have like a fixed dry max is based on some threshold value, which is 30 millimeter. But in the system now we make the dynamic dry max. That means the dry max based on each season. And also we introduce, we already have the flexible format of forecast, but we kind of changing that. So I'll come back on that also. So being on that background, this is the pictorial representation of what I'm going to talk today. So as I said, like, instead of using the raw model, we are actually calibrate the model. So we actually calibrate each of the NMME model based on the observed data set. And after calibration, the assumption is like each model has equal scale. So instead of giving the kind of skill-based weights on the MME, we just go with the simple average of the MME because the assumption is like we correct all the model. But we also do some smoothing. And there is some reason behind that, because this method we are actually, because we are not adopting kind of principal component or UF based system, we do some other system at each grid point. So each calibration is independent for each grid. So we need to do some kind of mathematical smoothing to get the information from the other grid. I'll come back each of the that things, but before that, it may be a reason, like, people may ask like, okay, so you're doing something on NMME, but CPC also do the same thing. The CPC also change their seasonal forecast based on NMME. So what's the difference then? And why we need, like, if CPC already have IRA, just, take this thing and make some fancy map. But there is some reason behind that. And that was like my first question to my supervisor that time, Andrew Robertson, that why, Andy, I'm doing the same thing which already CPC already started. So what we found, like, CPC also have the probabilistic forecast, and they also have a calibration forecast, which I'll come back on that. So first, I just to explain like how they make the probabilistic forecast. So this is a simple method. Like for example, each NMME model has different kind of ensemble size. So we basically, like, they basically count like how many members fall in a different category, which here like category is 3 because we are talking about similar focus, like how many of models are falling in a 3 different category, and just calculate the using the simple equation like of the probability, like where small m is the number of members falling in category, and capital M is like total number of member. So on that basis they calculate the probabilistic forecast. But they also say do some calibration, and the calibration method they call is PAC, is developed and invented by Van Doel and Emily Baker and also other colleague. So the PAC method is very interesting method, and when I read this paper I feel really interesting because as I'm basically a statistician, so I just try to understand the philosophy behind each calibration method instead of just using it. So PAC is a kind of same concept of ACC, which is anomaly correlation coefficient. So that means it's actually a correlation between the probability value P from each model, and O, which is dichotomous. That means either it's 0 or 1, because from observation we can calculate whether this has happened or not in the past. So then this is like a correlation between probability and dichotomous. And then what they did, they actually did the regression for each and every category from those probability P's. For example, let's say we have 3 category and we have like 0.3, 0.4, and let's 0.3 in 3 category. So independently of each category, they did some regression between those values for each year. Like 0.3 is one value, so we have like 30 years or 28 years. And also we can actually have the observation falling or not. That means we have a series of 0, 1, 0, 1. And also we have a series of continuous data, which is between 0 to 1 probability. So they did regress independently for each category. But when we do this kind of things, there is a problem. There's a certain like mathematical problem, because this is it's not like a basically a probabilistic approach to make those regression. There's like a linear regression approach. So there is a chance that any kind of probability go beyond the limit, like it can be beyond 1 or it can be beyond 0. So at the end they also like finally they adjusted the probability based on because this regression based on 3 different category, there is no information between what happened below normal category to above normal category. So after getting the probability they again correct it. So it was good, it was fine. But what I found is it's very, first of all, it's very interesting. But what I found, like, to try to understand, like, basically we want to do the categorical forecast. So either yes or no kind of forecast for each category. And our input is GCMs. So instead of calculating the probability in a non-parametric way, counting method way, we can actually using those GCM output and convert it in a probability. For example, we need to forecast 0 over 1, and we have a data from anything between 0 to let's say 300 to 500 millimeter based on the rainfall. So we can actually fit a regression, same thing like they did the regression between the probability and the 0 1 value. But the problem with that kind of regression, as I explained last slide, is kind of violate the assumption, because the assumption is the linear or the Gaussian. So it can be go beyond 1 or 0. So on that situation, we need to do some kind of a sigmoid function based regression, which is popular as logistic regression. So the logistic regression has the bound that the value cannot go beyond the bound of the predictant, which is 0 or 1. So on that, we can actually set a logistic regression based on the climate model's output itself, which is a raw rainfall data, and then convert it in probability. So in that sense, logistic regression is very fruitful because it's a, first of all, it's an alternative Gaussian approach, and the probability itself a predictant. Like earlier, what happened, like we can actually do the principal component or any kind of deterministic method to correct the deterministic signal and then convert it in a normal distribution. So it's a like two-way. But in logistic, it's like one go, because the predictant itself a probability. And also, logistic regression is considered as a machine learning algorithm because we are actually using the classification algorithm, because it's a question of classified the data whether or not, or we can actually increase that classification based on the machine learning method. So that's what I really interested on that method. And obviously, like there's no assumption of homoscedasticity or linearity or normality. So I thought, bingo, I got the method. So let's start with that. But the things was not so easy. So let me explain. We need to modify the method. The reason modification is like, again, logistic regression is a regression that we can actually regress for each category independently, just like PAC. Like, we can have a probability from, sorry, we can have a data from the GCM, then we can actually fit the logistic regression for probability of greater than or less than 33 percentile, which is below normal. So we can actually independently fit those logistic regression for each category, in three category. But again, the same problem will occur, that we can ended up with a bunch of uh, probability like we can get some bunch of probability which is like, if we add up them, it will not, maybe sometime it's beyond one, or we can't get a full distribution, because we need a full distribution to use uh, some kind of application that I will come back. But why we are not only constant our forecast system for three category, we need to go beyond that. And also there is a problem mathematically, that those equations are not constant to be mutually consistent. That means like, if we calculate those regression for each quantiles, and we can ended up with this zigzag value, which is like, there is a chance that probability of 10th percentile may be higher than probability of 50th percentile, because again, there is no information between each of a category like PAC method. So the solution is we have to modify this method. And the way we have to modify, what we have decided, and based on Wilkes' paper, we actually add a function which is based on the all quantiles. So basically, we're actually changing the simple logistic regression to the multinomial logistic regression, where we have a obviously several predictors and several predictants, because instead of just having whether or not for one or three category, we can have the whole distribution. And doing like doing that kind of things, we also like in solve that problem of not mutually consistent probability. So in that case, you can see a nice parallel lines from each of the quantiles. So there is no way that quantile of 10 probability is greater than the quantile of 50. So in that way, we kind of modify the basic method, which is logistic regression, but including more variables and changes to a multinomial setup. So based on that, we decided to go with the calibration method. But as I explained earlier, like we need to do the spatial smoothing. The reason behind that, like this is a one example for some probability forecast for some years. So it's actually the yellow to brown is below and green to blue is above. So if you look this map, it look very like a sporadic, like a mosaic kind of map. Like each grid behave different. Like there's a lots of independent grid, and there's a lots of incident when you can see like one grid is below normal, but the neighborhood grid is above normal. So taking decision based on those kind of scattered probability is always tough, because there is no information from the other grid point, because each grid point we fit this ELR and we have a probability. So we decided to go beyond that and do some kind of smoothing, and we tried different kind of smoothing, and we ended up with kernel function smoothing. And the size is 9 cross 9. It's again like we start with very small size, then we go beyond that. And also one thing we have to remember here, because this is our real-time forecast system, so we cannot do like too much sophisticated method, because then it will take forever to run, because we run this thing each month around 8 or 9 based on when the NMA model come. And the new system took nowadays like 3 hours maybe. But like before, when we started this method, it took like sometimes 7 hour 8 hour, because those correct with calculation of each grid, and then we did not do any smoothing. So based on that, we do this kind of things, and now we have kind of a smooth probabilities. So if we compare the left and the right, extreme right, you can see the smoothness and how we get rid of that. But the question is again, like, if we do the smoothing, can we lose the skill? Because the skill is also important, because we have to check whether our calibration method added any value compared to the non-calibrated method. So here is the example. I use the rank probability skill score, which is a kind of mean square error in terms of probability space, but combining all three categories. So this is an example of May start JJA forecast from actually hindcast from 1982 to 2010. And the left one is original. Original means just using the ELR for each grid point and calculate the probability and then compare with the observation. And the right side is the smooth, like we just add this kernel function. And anything beyond zero or greater than yellow, greater than zero, the skill is acceptable, which is actually telling us that our forecast is better than the random forecast or the climatological forecast. In this case is 1/3. So what we found, that skill is retained. So we are not losing any skill while doing the smooth. In fact, some of the cases, the skill is improved, because we are actually get rid of the small variability. And if we calculate the average skill for whole land point, and there is almost same skill, but like some improvement which is not statistically significant, but again we are not losing any skill. So based on that, we thought, okay, so we can go with the smooth. So now the system is like we calibrate each model with DLR, then average it as MME, and then final forecast we do this. For final forecast we are doing the smoothing. Again, we also do kind of different kind of aspect, like whether we do the smoothing first, then MME, or MME first, then smoothing. So we ended up with like smoothing at the end, because it again there is no significant skill improvement. And also if we do the smoothing at the end, then we again save some computational power. So based on that, we make the forecast, and obviously we save, like before we release the forecast, we do all those kind of skill assessment, other things. And the skill assessment now is live. So if you can see in IRI, if you are familiar with the IRI map room and data library, you can just go there and you can see the skill based on this method. And I mean, well, like that time we are using 8 or 9 NMME model, and every season we provide the skill for next 4 season. Like for January you have a FMA, then MAM. In such a way, it's just go for rainfall and the temperature. So that's live, so anybody can check the forecast system. So now the question is whether doing all those mathematical sophisticated things, whether we can get some value or not. Therefore, we compare our ELR method with the counting method. The counting method is the same, like again, like counting the members for each category. So that means like uncalibrated forecast, just using the members to get the probability. So this is one example for OND, like October, November, December season, making the forecast at September, which is lead one. And the left one side is counting again, and the right one side is ELR and RPSS. So if we look very thoroughly in those two maps, we can see very interesting features, especially in the left-hand side. The colors are very bright. Whether it's a red, if it is yellow or red, is very bright. If it is blue, is very bright. So that means whether like the model has like wherever you see the deep blue, that means this model forecast is worse than your random guess. That means this system does not have any reliability. In fact, the random forecast has more reliability from that. That means the forecast skill is very poor. But again, wherever there is a scale which is yellow and reddish, that means our forecast is better than the random forecast is very strong. But when you do the ELR, you can see that that brightness is kind of dump. Again, is one is good news, because when you see that all blue or deep blue regions in counting is became either light blue or near to zero. So that means we are get rid of all by like random scale or like the bad scale from the model, and this calibration helps those forecast to converts to the climatology, because RPSS 0 means equals to climatology. So we are getting rid of those bad scale from the model, but at the same time we retain the positive scale. But as again we are doing the calibration and try to convert those probability to the climatological probability, the skill score, although it's there, but the magnitude in some cases is actually deteriorating. But that is not in a significant way that we can say the skill is much worse. The skill is there, maybe like from 0.52 it's become 0.5 or 0.48, but still the skill is there. And also we can calculate the reliability. So this reliability diagram actually doing for a whole globe and pulling all the data and all the forecast. So you can see the reliability improve at least from each of the category. And one thing is very interesting for me, like when I see the improvement is the near normal category, because the near normal category is always a tough to improvement those scale, because we don't have much signal from the near normal years, because we have a signal from kind of anomalous year, whether it's based on ENSO or something else. But the normal year predicting seasonal focus is always tough. And if we compare those reliability, the reliability also improve in the normal year. So that's for the rainfall and for a one particular season. And then you kind of continue this kind of things for all forecast in lead one. And beyond RPS is we are also calculating some other skill score, which is kind of same philosophy, but explaining the different aspect of the forecast. For example, logarithm skill score or G-rock. So as you know, the generalized rock telling us like whether our forecast has a discrimination between the category or not, and anything greater than 50% will be good. So we kind of have kind of a usable forecast scale in terms of rainfall using this method. And then we thought maybe because rainfall is not at all Gaussian, although we assume that seasonal rainfall is Gaussian, so we kind of using the Gaussian technique. But we only have like 32 years or 29 years based on the hindcast. And we have seen that there's no, like, if you plot the histogram or any kind of things, you can't find any Gaussian uh, pattern from the rainfall. So that for that we can conclude that this method, which is non-Gaussian, is actually working for the rainfall. Now coming to like up to now we show the real-time skill, sorry, the hindcast skill. So now we also like verify the real-time skill. So I just want to show one example which is very current. As we know, like we just ended up with the monsoon in South Asia, which is from June to September. So this was like a real-time forecast, and just zooming over the South Asia in month of April and in month of May for JJA, and also the same thing for Italy 2, which is JS. So what happened when we see this kind of rainfall, we kind of because it's very strong. The earlier there is always a complaint from our friends from South Asia that we don't get much signal from IRI forecast. There is always a white. So this, like from 2017, we get more of the signal because of NME model and this calibration. And this time we got like a really big signal in terms of signal forecast. And we communicate this forecast obviously in real time. And also we presented this forecast to the South Asian Climate Outlook Forum conducted by WMO. And we are kind of confident, but still we don't understand the pattern, because the pattern shows is very interesting. Because wherever you see the the more above normal signal is actually not the monsoon core region. So monsoon core region somewhere in the inside, like in the center of the India, and the western part and the southeastern part is actually a region where we did not receive more rainfall for the season, because the western part is weaker, the monsoonal flow, and that southeastern part has a rain fed because of the topography. But this is the real time map generated by Indian Meteorological Department, and this year is actually very interestingly like our forecast captured this anomalous pattern. Like if we talk about the all India rainfall, it's obviously like above, but it's not important to like produce or all India rainfall, because rainfall has so much variability. It's always better to have like better to capture the spatial variability, and this time it's captured. And this is like one example. We also see that real-time forecast over the Africa, over US. So most of the cases, our forecast is kind of in the right signal. And obviously, wherever the signal coming from the ENSO, our focus is always capture the signal. So this is for the three category forecast. Now I have to talk about like some other representation of the forecast. As I explained earlier, like three category forecast is good. People use it. But for actually using in a planning or taking a decision based on three categories, sometimes is not so worth it. Because for example, like, people from the disaster risk business, people from the agriculture, or people from the hydrology, they want to know like what will be the probability for certain threshold, or what is the probability of certain rainfall values, or can you give me the whole distribution, then we can actually compare with our old past forecast or our climatology. So based on this method, we also develop this method. So the way you can find it in our main page, in the right hand side there's a link said go to IRA flexible forecast, and you click there and we ended up with this. Let me explain a little bit. So for example, this is our three category forecast for Africa. So on that flexible, if you click any point, then you can get the whole distribution. And the black line here is the climate. That means like what was the climatology on that for that season. And the green is actually the forecast. So you can actually also compare whether the current forecast is above or below or drier or wet, depending on the season from the forecast. And as I said, like there's a lots of application of this forecast, and one simple application I can explain that this is a tool which is developed by our financial instrumental team at IRI, those who are working on the forecast-based financing. So what they have done, like using this flexible forecast for Malawi, which is a country in Africa, they make a tool which actually explain the climate triggers or shocks. So depending on the probability, they make different triggers which help the disaster management to release the contingency plan or not. So that was actually a real-time application of those kind of forecast system. So up to now, I discussed about like, mostly on the rainfall system and how we develop, and we ended up with kind of satisfactory system. But now question is like whether this method is as good as in other variable like temperature. So first of all, like this is kind of who's are familiar with the IRI forecast. We used to have this kind of forecast all over the red using the old system. But with the new system, we got a interesting pattern of the forecast. So again, we have the red, which is above normal signal, mostly on the subtropics. But in the tropics or in the southern hemisphere, the signals are not like so strong. Sometimes we got some below normal signal. So that was like when you make, because mostly when you prepare any kind of forecast system, the first thing we look at the rainfall. So we don't even think about, and we thought like, okay, so if it is work for rainfall, it should work for temperature. And that was our assumption, and that was not a correct assumption. Because when you see this kind of system, we found like, okay, so we get rid of a more above normal signal, but what about that? And it's kind of persistent for all season. So then I look beyond uh, the forecast and try to understand the system, how it works. And again, I compare with the counting method, which is simple or non-calibrated, with the ELR method. And as we have seen in the rainfall, that counting method, there is some skill, there is no skill, but ELR kind of retaining those skill and get rid of a bad skill. But in temperature, first of all, like obviously ELR get rid of all blue, which is good. But again, the magnitude of the scale is is kind of very I must say, like, not a statistical significance, but by like at looking you can see there is like lots of damping. And also if you look this map, there is an interesting pattern. Like look over the Greenland, the scale is as good as both the method. We can compare like which is good, which is bad. But when you look for the other part, especially in the tropics where we get the kind of dumping probability, the scale is actually like decreasing from more than zero point 0.2 to 0.05. So that was like really concerning, and we don't understand like what is the reason behind that, whether it's a method or the model or something else. So then we said, okay, look at the real-time forecast. And if we do the real-time forecast with the counting and ELR, again, the counting is look like the old forecast system because it's very strong signal. And although sometimes we get some below normal, but it's a very strong signal all over the world. But with the new system, again, we get this pattern like subtropics is always high and tropics and southern hemisphere, there is no kind of significant probability pattern. So on that, we start thinking about whether this non-Gaussian method works or not, because in principle, temperature is a Gaussian variable, especially in the seasonal forecast. So we thought about that and we thought, okay, so let's do some kind of synthetic experiment. And what we have done here, we kind of take the random number from the Gaussian distribution and feed the ELR. And we kind of try to understand whether that logistic regression is actually regress properly the data which is come from the Gaussian distribution or not. But we found a very strange pattern, because if it is in 45-degree line or diagonal line, that means like Gaussian and ELR is actually uh, kind of good associate. But we don't get that kind of line. We kind of get some kind of spined line, and we thought, okay, so maybe the ELR is not right choice for the Gaussian distribution. So that may be the reason that we need to do some other kind of calibration system for temperature. And for that, we go back and we start with, okay, so we should do the whole system. But here, what we have done, actually we correct that each model based on the regression, and then we kind of convert that deterministic regressed value in the Gaussian distribution, and which I call OLS, which is ordinary least square method. And for like, I just zoom over India and for particular season, because DJF is that winter season. And again, if we compare like counting ELR and OLS, you can see like OLS obviously get rid of most of the blue line, blue spot, which is bad for like not good focused. But again, if you compare the brightness or compare the magnitude of the red, which is very highly good forecast in terms of RPSS. Like still OLS is not as good as counting, although OLS in some point is better than ELR. So that is again a like, we thought like it's maybe because of the Gaussian distribution, but now we again confused. It's maybe not with the Gaussian, but then we thought, okay, so look at CPC's calibrated and non-calibrated forecast, and plot our own forecast with new OLS and look how it looks. So again, the counting is like counting the members, and this is like same as CPCs, and although they plot in different way, but you can see like mostly like yellowish, which is our reddish fat pattern of the forecast. But this is the pack, which is again kind of a regression based method and OLS, and we found like that wireless and PAC look very similar because it retained the signal over the tropics, which is actually we lost in the ELR, and also from the southern part. So, in terms of real-time forecast, because all the question come from the real-time forecast, like why we expect that kind of forecast in the tropics and the southern hemisphere. So at least OLS, which is again the skill score wise not so good as the non-calibrated forecast, and I'll come back why it is. And but it actually retain those probability, which is not at all very strong like counting, and look like same as back. And again, like, coming back to the skill score in calibration and non-calibration, like some point, like the non-calibrated focus is very sharp. Like, we can get the probability up to 70%, 80% from the models wherever there is no much signal. But whenever we calibrate it, that which actually kind of push it to the normal or towards the climatology. So we never get kind of a very sharp probability in seasonal forecast unless this region is highly correlated with the ENSO. I'm talking about where we did not get much teleconnection, that area. So in that sense, we thought maybe like although OLS is not in terms of the hindcast skill as not as good as counting, but maybe OLS is better to represent the forecast. Then we try to understand like what the other people doing. And again, like our Tony and Mike, they have published a paper based on kind of same concept. Like they're doing that canonical correlation analysis, which is again a spatial correction based on UF method, and then convert it in a normal distribution. And there they published this paper, and based on the same set of NMME model, and their conclusion is something different, and which is interesting from my case. Like for example, this is for a particular model and a CCA correlation. Like after doing the CCA, they plot the correlation values, and this right side is like the same thing without any correction. So if you look in some area, the non-correction method is much better or as good as the correction. But some area there is obviously the skill improve. But if we calculate that how much skill improve based on the CCA and non-correction, there is not much area we can say that there is a huge improvement. If we also like make some boxes, and we can see the last column of the box, that is the skill changes, which is almost negative. So that means this is not only the normal distribution assumption, there is something else going on in the temperature forecast, that the other method also did not get much improvement when we do as a post-processing. So that helped me to think, is the trend is the background of that, whether the trend is something that we actually totally forget about when you do that kind of calibration, because we know that because of climate change the temperature is changing. So these, I'm kind of thinking on that regard, and still the work is going on, when we found a very interesting paper which is published just August. So what they are doing, they're trying to embedding this trend using the Bayesian joint probability method. So and they try to, although like the GCM is different, it is actually they are using in a system 5 BCMWF method, but they try to incorporate the trend. And on that, I thought, okay, let me plot some random point over globe and see whether the trend come from each GCM as compared to the observation. And as we saw, like the skill is kind of a skill, and the probability is kind of dump in the tropics. So I take a one point in Africa near Ethiopia, and I plot from last hindcast. And this is the GHCN CAMS, which is our observed reference, which we use for the calibration. And we get some kind of trend, which is not very sharp. We get some trend. And these are all NMME models. And the CANSIP is the current one, the current Canadian model based. The CFS has some trend. NASA has some weird temperature pattern for some of the years. Again, it's I choose any of the random period. Again, NCAR doesn't show that much of trend. So what I found, like that may be the new avenue we can work on, that to try to incorporate whether the GCM has a trend the same as observation. If it has trend, then whether the trend is very compared to observation is very high or not. If they don't have trend, for example in this case like CSM or CANSIP, how can we incorporate those trend and doing this logistic regression. So that was again an open-ended question, and I kind of obviously looking for advice from this seminar. So that was like the way we kind of approach the problem. Instead of just doing something, we just see each and every cases. And one interesting thing what I found, that the null hypothesis or the assumption, we always go with, like, using some post-processing method based on some rainfall or some other variable, and using the same post-processing method for the other variables. That may not be the right way. We maybe think about having a different post-processing for each of the variable. Again, there is another challenge. It is not only the challenge for the temperature, there is another challenge is to produce this real-time forecast using the NMME model, because some models are changing their version, some models are not in real time. So whatever the skill score I have shown you, that's a set of some model. Again, when the model changes, everything has changed. So it's kind of a dynamic system. We cannot just fix the program and run every month. We have to check each of every GCM, whether it's coming or not. And then also there is a question about whether the number of predictors, like sometime whether we lose the predictors and we lose the information. For example, for the sub-X, for the sub-seasonal forecast, we're using the sub-X model. This month, we just only get the 2 model instead of having 3 or 4 model. So these are like all real-time challenges, but we have to incorporate in any case, we have to make some dynamical system that it's go beyond these challenges. So I can end my talk on that. So what we found from this exercise, again, this is not only the academic exercise, it has the application value. So we found that extended logistic regression method, which is non-Gaussian method, is actually working for rainfall. And this is actually more robust method based on compared to the Gaussian assumption. But that might not be the good for temperature. However, we don't even know whether this is just only for the Gaussian assumption or the other factor, which is trend. So we have to look very thoroughly, and I'm working on that to find out some different approach, maybe incorporating the trend in decisional focused to find out this problem. To find out the solution in this problem. Thank you.
Thanks very much, Nochi, for that talk. I think a lot of us are thinking about prediction on different timescales, so it's always useful to see application of new methods. So if you have questions, you can type them in the chat, or you can use the raise hand feature in the participants window. I see we have a question. Is that Bill Large?
Yes, could I ask, I've got 2 questions actually. The first one concerns your suggestion that for different variables or predictants, you would use different post-processing. And have you thought about the dangers then of actually forecasting unrealizable states? Now, it's possible even with the same method, but when you start, using different techniques for different variables, the forecast could in fact be an unrealizable state, the way the 2 different variables show up, like lots of rain with very low relative humidity or something like that. Have you thought about the dangers of just willy-nilly going through and changing techniques from variable to variable? That's one. So maybe you could answer that.
Okay, that's a good point actually, because we should have some kind of information between those variables, which is actually dependent, as you said, rainfall and temperature. But one good thing in this point, because we are not actually doing any kind of data analysis modeling or empirical modeling, because those output come from the GCM. And when it's come from the GCM, it's already take care of that kind of system, because it's come from a synthetic weather, synthetic climate. So that case, like because we are applying post-processing for a forecast. We are not generating the forecast. So it's there already, right. The information already there. But again, as you said, that yes, we have to think about that. But my point is, like, from the post-processing point of view, we have to think about the characteristics of the data. Like if it is following certain distribution, and if we just using the other distribution because it is works for other variable, and we just implement it for other like same system for another distribution data, we may miss some kind of information. And that's what we saw, like, if you remember the probability in the tropics, we did not get any strong probability if we use the non-Gaussian. But if we change the Gaussian, at least we get some information. But that's a really good suggestion, really.
So the other question concerns the number of steps in your processing, and instead of just looking at the end result, trying to think about verification of each step. And then one of your comments was you were using probability became a predictant, correct? Mm-hmm. How would you do any verification of what you were getting of probability?
Mm-hmm. Yeah. So
as that step alone, just that's all.
Yeah. So basically the system we're using, like, the predictor is a category, like, whether or not it happened. So this logistic regression giving us the final result is probability, which is the probability of whether this category happened or not.
Correct.
So you're talking about how to verify this probability. So So there's a number of ways. So first of all, in terms of the model fitting, we can do lots of goodness fit of tests, like, archaic information technique or Bayesian information technique. So that was like the fitting in terms of things. Again, if we verify the probability, as I explained already, like, we have lots of other verification system like rank probability forecast or reliability or ROC. Those system actually help us to verify probability compared to the observed frequency. Because here, instead of comparing two time series, we are comparing probability and either or not event happen. So we are actually using those systems to compare our probability. I don't know.
Questions? Dan, go ahead.
Thanks. I was wondering, maybe a related question about, so it seems like in these maps, there are, regions where you have skill a lot of the time and others where you don't. I was wondering if, as a part of these forecasts, if there's uncertainty quantification that you provide about how reliable they might be. And then maybe a related question about whether some of these tools could be used to inform the composition of your ensemble, and maybe which of the models is really contributing most to predictive skill.
Yeah, that's great. Great question. I can start with the last one, like whether you said like which model contribute more skill or not. So the assumption is like, we thought like after calibration, each model give the same kind of, same skill. That means like we are correcting the systematic bias. Although like after the correcting the systematic bias, still, although we assumption, but in real time, each model look different. And we are actually looking at that. But what happened in the real-time forecast system, as I said, like we always have the limitation of losing models because of the model change their version and or they stop producing the forecast. So in that case, we cannot make the weighted multimodal system, first of all, because if we lose the model, there is no way we can get the model system. And also, we only have like 28 years or 30 years of hindcast. And based on that, giving the weight is always a matter of overfitting. So that, and as we already kind of corrected the model based on the systematic biases. So after that, if we started making the multi-model based on different weight, it may be a little concerning because of the time period. So that's what like, but we saw the different skill, and that's what like, when I plot the trend and I see like, different model shows different thing. And also same thing for the rainfall, like we see some of the, we kind of, up to now, we kind of get some idea about different places, which model is working on which model not, but at the end, we have to make them multi-model. So that was the second. The first question you asked about the uncertainty, right? Like when you said like, okay, so yeah, we obviously convey our uncertainty, and that is the reason that we put our skill map in the website openly, because there's no hide. Like whenever we keep the forecast in the website is written everything like what is the verification, and we also have the real-time verification and IRI system starting from 1997. So anybody can look that and take the decision whether they go for or not.
Got it. Okay, thanks.
Still have time for a few more questions. I had a question. One of the points I found interesting when you were showing the maps over India, and you pointed out that some of the skillful areas did not necessarily match up with the major monsoon areas. So I'm wondering if you could comment on that a little bit more, and maybe also what you think about the timescales for predictability specifically for the South Asian monsoon.
That's a really good question, because my expertise on that. So whenever the monsoon started, I start looking on that. So what happened this year, when you see like, those area like Southeastern Asia, Southeastern India, and the Northwest part, which is basically dry climatologically. So what happened, because this year the Bay of Bengal have lots of depression, and it was not like a single incident, that because sometime what happened for a single incident, actually if there is a lots of rainfall in 3 days and climatological it go beyond the above category. But this year, because there's like 4 or 5 incident happened, where the lots of depression happened in the Arabian Sea, which is actually cross the western part of India. In fact, it's crossed diagonally. For example, it's somewhere here and then it's crossed from this side. So it has lots of rainfall because of that. And this is mostly in the subseasonal scale, which is contributed in the seasonal scale. So we have also, because we have the subseasonal focus system. So wherever we found any kind of signal in week 2 plus 3, 3 plus 4, we are kind of communicating with our partner in India and Bangladesh and all over the Asia. And also this time, not only the Arabian Sea, the Bay of Bengal is also very active. So that's what you see, like, lots of rainfall over the eastern part of India and, northeastern part. So that is interesting, because we kind of, we are not, we thought, because this year is also getting, that time, April and May, we kind of not sure, but we know there is a signal of La Nina. And we were expecting that Indian monsoon will be more rainfall this time. But I was wondering about the spatial patterns, because if it is like La Nina pattern, then obviously the monsoon core region will be more than this rainshade area, sorry. But I think this is that the reality, that subseasonal characteristics, especially the monsoon depression, has a lots of role. And interesting, like seasonal forecast capture it. And when I see the RPSS, like what is the skill of the RPSS, skill of the IRI system over India, it's interesting. The RPS is also improved, like mostly strong over those area where we expected that above normal rainfall. But we are kind of right now we are kind of in preparation to make a report on what happened in our seasonal and subseasonal forecast, whether we can capture those signals or not, working with the Indian Met Department and thinking to hand it over with that. So thank you, Katie, for this question.
Great, thanks. Any other questions? Well, I'm not seeing any more questions. So thanks very much, Nochi, for that presentation. And next week, we're going to hear from Nathan Mueller, who's at Colorado State University. So thanks again.
Thank you, Katie. Thank you, Tracy. Thank you, everybody.